Good afternoon. I'm not sure if this slot is better or worse than the one before for people nodding off, so try your best to stay awake. This is a story. It's our journey of how we've transformed as a company from delivering what we delivered previously towards delivering more container-based solutions to our customers. It being a journey, it got a bit of a beginning, where I'll explain where we've come from, what we do, a little bit about what we actually are as a company, and where we've ended up today. I should say I have a habit of speaking too fast. If that's the case, please shout or wave. And if I'm not speaking loudly enough, also just give us an indication and I'll speak a bit more. A little bit of background about myself. So as I've already introduced, my name's Daniel Laird. I started life out as an embedded software engineer and worked with Philips Semiconductors and NXP Semiconductors, developing embedded software, in this case for televisions and set-top boxes. And some of this becomes more applicable later on in the slides as to why I've called this out as useful. Back in 2009, we finished working with Philips and NXP, and so I joined what was then Ericsson, and I joined again as a software engineer. In this case, I switched from one end of the spectrum, which was the set-top box and television end, to working at the other end in the media sector, which is the equipment that sits in broadcast studios, outside broadcast fans, that kind of stuff. However, my role's changed, so now I'm the head of software with Mediakind UK, so my role's changed a little bit. I don't get to write quite so much code. I try, I irritate the developers, they peer review it and try their best to be polite. But my main role now, as you can imagine, is actually helping us on our journey and how we transform. That's been in both the ways of working, all the obligatory buzzwords of becoming agile, etc. That's the kind of slides I have to present. And some of the technology choices that we're using as we go from bespoke, custom hardware, where we came from, to delivering more cloud-ready solutions for our customer. Now, maybe some of you in this room have some idea who Mediakind are, but that hasn't usually been the case when people have done talks at these events, so I thought I'd give you a brief overview of who we are. So the roots of us are from Tamberg Television, which was acquired by Ericsson in 2009 as they tried to move into the media sector. They then acquired the Microsoft Media Room business, which sort of addresses large cable customers in the US, Azuki Systems, a sort of cloud data aggregation service. And as they continued building what they thought was a media portfolio, they acquired Fabrics, which is a cloud DVR solution, so recording stuff in the cloud and then streaming it to set-top boxes, no need for local hard drives. And finally, a company called Invivio, mostly based in Rennes, and for them, that's a software processing based on sort of Intel hardware to provide, again, broadcast-specific features to our customers. This time last year, Ericsson spun us out as a separate entity, so we're now Mediakind rather than Ericsson. What is it that we do? I've spoken a little bit about it. I was asked to put in the obligatory marketing slides so that I could show you all what it is we do. I could try and talk about this, but I'll highlight the two major points just to give you an overview. The most important point to take from this slide is you are in the middle of what we class as our universe, the consumer, everyone here. And all we are focused on doing is delivering video to the consumer, be it on any mobile device, TV, whatever. That's the purpose, that's why we exist. It is to get video to you, however that happens. And if, as I suspect most of you are watching television, video at any point, there's a pretty high chance that it will have passed through one of our devices in some head end, national broadcaster or otherwise. So when I submitted this, and I had the idea that I'd like to do a talk at a conference, why did I think our journey was something that would be worth sharing with a wider audience? And it was basically for a couple of reasons. There are a huge number of examples on the internet of how people could be doing things, and there are even more when you get into stories about how are you going to transform your organization or your business to move to the cloud. You get things like microservices architecture, and you push it a little bit further. Everything will be Dockerized. do these things, your business is sorted. But behind these things, there seemed to be a common set of threads, which for me in my role were an issue that needed to be addressed. The common key assumptions, and it's not always the case, but the common key assumptions that I sort of observed were in many cases these examples of how you could be doing things made statements which indicated they either had a limited customer base or a couple of really large customers that they could handhold through any kind of change process that they were attempting. The indication that they had limited customers or sort of startup cultures with sort of a smaller number of customers meant they also had limited support requirements, or they had customers who were prepared to just take releases all the time, bugs or whatever, in the belief that progress was always going forwards. And the third thing was there are many times when you say, if you just start from here, it'll be really, really easy. As you can see from the slide going back a few, we were a combination of 5 companies acquired over 10 years, millions of lines of code, some of which actually do the function we want, some of which we're not quite sure. But this indicates, they believed that you could just throw it away, start again, and design your application. Our experience as a sort of company, we had a large existing customer base, and those customers were across the world, some of which had very strict and very long-standing support agreements. This is broadcast hardware. This is the big national broadcasters. They can't go off air. If they do go off air in something like the Super Bowl, you don't want to be the person dealing with that outage. And as an engineering organisation, 2 things were pretty clear to us. One, we had no desire to start again. As an engineering team, why throw it all away and start again? The engineers believe that's wasteful. And, as you might imagine in any sort of software company these days, we didn't exactly have engineers sat around doing nothing, so we didn't have the capacity to just do it again in parallel whilst we kept all of our existing customers happy. So, why might this journey be of interest to you? Why our specific sector? Well, I thought that in our case, we used to think we were so different to everybody else. Broadcast is special, it's different, it's unique, it's critical infrastructure for companies. Nothing will change here, we're in control of these things. So we designed bespoke hardware. By this I mean we had hardware engineers designing PCBs, we designed chassis, we did thermal checks, we designed plug-in modules, wrote software, delivered that software to the customers, and it achieved the required encode performance in whatever environment they might operate, be it Antarctica, where it needs to operate in 0 temperatures, up to people in the Middle East, where it has to operate at +50. The broadcast sector had sort of custom data connections. I've called out a couple here if anyone sort of knows the background, but ASI, SDI, primarily to get uncompressed video around data centers, so just sort of BNC, sort of coaxial cable to do high data rate transfers. And, because we're different, because broadcast is special, we had specialist support engineers who gave themselves the titles of broadcast engineers. We had some of our own, our customers had some of their own, and they were paid a premium as opposed to IT support engineers, because broadcast is special, IT was generic. So you ask, well, what changed in the broadcast sector? You can probably guess where this slide goes. Software performance. We're not immune to it. Very few of us have been, and even when we thought we were, it keeps moving forward. So why should we spend all this time and effort designing custom hardware, using FPGAs to accelerate sort of encode a video, when if we just wait 18 months, Intel will just give us a chip that does it for us and we can carry on with our lives? The second thing that changed significantly for us was our customers. No longer were they just big national broadcasters who were sort of protected by government organisations and could sit there without changing. These were telcos, your BTs of this world, etc., who were always competing with other people. And they had the desire, they wanted standard IT infrastructure. Why is broadcast different? They dared to ask the question and then challenged the sector. And of course, now they wanted to use standard servers, standard monitoring equipment, standard services. And, dare I say it, they wanted to replace their broadcast engineers with IT support engineers because it could just be another system for them to monitor. The primary goal in their case is obviously to lower their operating expenditure, but that's the customer ask, and we're there to deliver what they're asking for. So you can see broadcast got impacted the same as every other sector, is slowly getting impacted by Intel performance and the cloud. So, sort of the first step on our journey, if you like, is just beyond the bespoke hardware that we were shipping when we acquired Invivio. We started to ship what we call bare metal appliances. You can guess what these are: a server, which we'd provide to our customers with some plug-in PCIe cards to provide those custom data connections, be it SDI, ASI, for example. And it would have some kind of OS on it. In our case, most commonly a CentOS distribution. And that would be distributed as an ISO installer, like many companies, to our customers, or pre-installed at some factory. Then the magic, our application, the thing that actually delivers the feature that the customer wants, most often some kind of encode or transcode of video and audio. And throughout its lifetime, a set of security updates, probably not as frequently as anyone would like, but more frequently than we could manage. So we'd started to take this step, and we looked at how we might move from bare metal appliances towards the ask of our customers of, why are you not ready to move to the cloud? And we looked at moving to containerized deliveries. Now, initially, and I've taken this term off of the internet, it's a good way of sort of locating sort of people shipping large containers. They've been labeled as fat containers. Other people might call them their sort of VM-like containers. But initially, that was our focus of what we would deliver. And you might ask, why would we go to the effort of shipping 600 or 700 megabyte containers times however many containers exist within our deployment? Well, my role as a software manager and the R&D organization as a whole, we had to make some changes. What are containers? A starting question for your engineering staff. How are we going to deliver these? How are we going to deploy them? What technology choices are we going to use? And what runtimes are we going to use to make these work? Those questions can be answered and be sort of fleshed out, but just by using full fat containers. You don't need to optimize that early in your sort of change process. And we like to think we were taking some kind of agile approach. Yeah, we can worry about the size of containers later. Right now, we just wanted to try something, get some feedback, fail fast, repeat. A couple of customers that were prepared to take that step with us and push on. So we spent our time in the early days focusing on two things. We chose to adopt Kubernetes over some of the other orchestration platforms that were available at the time. And as an R&D unit, we started to learn how we might deliver containers to our customer. What does it actually mean to deliver a container or a product? So we made the conscious decision that shrinking, making these containers smaller, which is something that's written about quite extensively when you start typing in container deliveries on the internet, we made the decision consciously, we come back to that, we'll worry about that one later. So apologies, this is sort of pseudocode coming up, but your Docker file, I don't know how much Docker experience there is in the room, but essentially from CentOS 7.6, so a great big fat OS image, add in a couple of extra repositories, because what's more data in this container, copy in our RPMs, so we would download those from the Nexus server, so our sort of internal package manager, install them using yum, set some environmental variables, and more importantly, define the entry point for this container, repeated across the number of containers that make up our deployment. So some indication of the sizes at this time. So a Python-based container, typically containing one microservice, we were shipping something 570 megabytes in size, and our C++ containers were in the region of 520 megabytes. Large, not sustainable, but it was allowing us as an organization to learn and adapt. But one of the first things we realized as an organization, and as the engineers, essentially I'm going to say played, but that probably sounds slightly more relaxed than it really was, as they investigated, probably the better word, the first thing we realized is how much commonality there can be between different Docker containers. So I'm going to give a brief overview of my understanding of Docker layers. Again, I'm no Docker expert, but I've sort of used it enough to explain it briefly. So images are composed of layers. Layers essentially get stored on a disk and probably later stored in a registry. That's probably how it will work. And when you're writing some kind of Docker file, for every Docker command that you're running, be it some from line, run, copy, etc., a new layer will get created. What we learned as an organization is the following. Let's consider some kind of deployment that we might have. Ignore all of the infrastructure containers that will be here behind. You've got a Mongo database and some Redis databases and alarm managers, that kind of stuff. Focus on the three things that generally make up video for our customers. So video, audio, subtitles, sort of three primary goals of what we're trying to achieve. We've got teams delivering these, each of them based on a version of CentOS. And from our bare metal days, these are pretty uniformly the same. We didn't have teams using different versions of CentOS. Everyone had sort of grown up with, we pick a version, we ship that version. What version is it? It's the same as everybody else. And the teams each develop their own internal application logic. So the video team have got some code, a microservice or similar, that provides the video performance. The audio team doing some kind of audio transcode, and the subtitles team creating the ability to insert subtitles into your video stream. The important thing is, what does that mean for what appears on the disk and later in your registry? Well, the CentOS layer is common across all your three containers. So you can end up with just one copy of that on the disk, and then the three containers will pull that in. You have another three layers within the registry that represent the application-specific logic. And this, essentially, is what we can ship to our customers. Now, you might ask, why is that what you ship to your customer? And the reason for this is we don't ship a container to a customer, we ship a set of containers to a customer. But we live in a world where not every customer has their broadcast system connected to the internet talking to our Docker registry. They're pretty worried about security, someone hacking some national broadcaster to change the video offline. So they're behind a firewall. They might have their own internal registry service. We've also got kit in the back of outside broadcast fans, so doing the football, and they're never going to be connected. So they're upgraded from USB sticks plugged into the front of the servers. So we actually have to find a way to get containers to a box which can then be installed locally onto some kind of storage, and then locally within that appliance we can run those containers. It doesn't matter that it's not the cloud, it's just a cloud of one server. But if we take a sort of next step, our teams attend events like this, and they go to some exciting talks where they get told that they should worry about the size of containers. So the subtitle team make the decision, well, CentOS is ginormous, we're switching to Alpine, and all the stuff on the internet tells them Alpine's small, this would be brilliant, and they manage to make their container significantly smaller. But what it actually means for us as a company delivering something to the customer is we've now got another layer in our sort of set of containers that we're delivering to our customer. As a result of the subtitle team optimizing what they deliver, we've now got to deliver something even larger to our customer. So you have to be careful about what you optimize. So for us, as I've already described, we typically combine all of our container images to deliver. So sort of sudo shell script again. For a set of images, we pull them, and then you can use a Docker save, pipe it to some table. You've got some kind of archive file with all the unique layers available. And then at the other end, when you ship that to your customer and it's an appliance, some kind of script can put that into a local registry, either connected or otherwise, and your device can be upgraded. So the key thing here is to remember and focus on understanding what optimization might do for you, because it can have unintended consequences. The next thing, technology has a habit of moving forward. And as we started, the first version of multi-stage building was just sort of becoming commonly used. So we had Docker 1705, I think, introduced the concept of multi-stage building. So for those who haven't got the experience, it's pretty simple in that it allows you to, within one Docker file, define 2 steps or more, but in this case we use typically 2, where the first step allows you to collect all of your dependencies, all your RPMs, all your sort of scripting, And in our case, we continue to use RPMs because it's convenient, because that's how our company is set up, to install all of the application-specific code. The important bit, and I think Timo earlier touched on it in some of the talks, is you can then, in a second stage of the Docker file, define what it is you actually want to ship to the customer. Essentially, you can take a subset of the first part into the second stage and ship that to your customer. The result is a Docker file that looks a bit like this. The top half is the same as you saw previously, where you define a CentOS base image. In this case, we typically give it a label, so we say as builder. It's a fairly common sort of set of patterns if you look on the internet. We still do the same as we've always done, yum install packages if it needs dependencies, because we've added our own Nexus server. It's pulling dependencies that we know we can manage and we can monitor, and it installs them. The important part is the final 3 lines, where you essentially say from scratch, which is imagine a 0-size container, and you copy from some directory path, you can do other ways, but for this example, some directory path to this container and define the entry point. But it's this bottom part that defines the actual output container that's typically going to get labeled or tagged, pushed to your registry and shipped to your customer. The impact for us was pretty significant. Without a huge amount of effort, but with it being consistently applied across our containers, we typically took our Python containers from 570 megabytes into the region of 78, 80 megabytes. The examples look quite accurate. That's just because I've picked some examples and put them in there. The C++ container went from 518 down to about 150 megabytes, which when replicated across 25 odd containers that make up one of our deliverables was a fairly significant saving in what is actually being sent somehow to our customer. But, and I'm going to come back to my beginnings in the software industry, as we looked at what we were doing, we started to understand that containers are the new shiny thing, but our background, our expertise, a large number of the engineers we worked with were embedded software engineers. And embedded software, if you sort of, in many cases, primary function was to deliver something that was memory optimized, high performance, small, secure. This is something that our engineers had grown up with and learnt for many, many years. And we started to recognize that containers tick many of the same boxes. They end up being deployed on something not that you would class as an embedded platform, but the techniques, the tools, and what you're trying to achieve, a container should do one thing and one thing well. It should be small, matched very nicely with our background as embedded software engineers. So we started to look at how we might take some of those techniques, some of what we knew as engineers, and apply it, if you like, in the new world. So we decided to do something called Dockerize, a funky name. Now internally, we've written some scripts to achieve this. I'm going to give some credit to a GitHub project on there, and that was sort of some of the background and some of the sort of basis for it that we started with. But what is it? Well, for us, it was a way to, firstly, have a common way of building our containers, and secondly, a way to define how we were going to do that. So we have, within our first stage image, we have a directory structure that we trust and we sort of dictate is true across all of our building processes, with a directory called /image and /app/image. What we do is within our /image directory, we place what you would call, I suppose, common runtime requirements. So for our Python-based microservices, essentially our Python containers, we would put a standard Python runtime, some kind of number, whether it's 372 or whether we were on an older version. We'd also have one with our C++ libraries, so the sort of GCC runtime, glibc runtime in the /image directory. And finally, and Timo again touched on this earlier, containers, you're always told to take everything out of containers to make them as secure as possible. But remember, this is a journey. This is something we're living through. There's a lot that can go wrong, a lot that needs to be learned, and nothing will frustrate your developers, your ops guys, or your customers more than you saying, I can't get into the container, I can't tell you what's going wrong, leave it with us, we'll come back to you. So there are many Linux utilities that you want to have within your containers. Our background from embedded software was we'd learnt to rely on a tool called BusyBox. It provides about 300-400 standard Linux utilities, but in our case, it's a binary of about 800K. Are they all fully featured? No, but they are very capable at doing the essential sort of triage effort. So we put BusyBox into all of our containers at this stage. We then ensure that each of our Docker build processes places within the /app/image directory the application-specific logic. So that's the difference, if you like, between each of our containers. And the command line can be inserted into some kind of Docker file to do something like this, where you run the command. We specify some RPM ignore keywords. I'll explain why in a moment. And then we say we'd like to include a few directories, as is the journey, while we're including var log. We haven't quite got to the stage where we're dealing with logging externally, for example. And we've added some other useful utility functions for the developers. So JQ for handling some kind of JSON parsing, and curl, because it's always useful to have curl, and BusyBox doesn't provide it. So in a bit more detail, what does it Dockerize actually do? Well, I've already described that it copies stuff within the first stage process into two known directories. We then do something that, again, as embedded software engineers, we do every single day and have done for the last 20, 30 years of our lives, which is use something called LDD, which will scan executables and tell you what the requirements are in terms of shared libraries. So you don't guess what libraries you need. You don't just take the /lib directory because you know you need something from there and you can't be bothered to work it out. You take the ones you actually need based on the metadata, essentially, within the binary files. And as soon as you do that, you can use something like strip on each of those SO files to make them even smaller and remove all your debug information. Then we do something which is where we create an RPM database within each of our containers. Now, if any of you were attending the Timo's talk earlier in this, you might say, why would you do that? The reason is to do with security. Customers use standard IT tools, some paid for, some otherwise, and many of them use things like Claire to scan the data container and determine what known vulnerabilities you have. Most of the free versions, and I think most of the paid for versions, rely on talking to a package manager to say what's installed in this container, what version is it, what vulnerabilities do you have. If you don't have an RPM database in your container, the customer can't know what the CVEs are easily, and then their IT departments just have a default policy of we're not accepting that, we don't know what the risk is. So we scan the things that are in our second stage, and we manually create entries within an RPM database so that when they run Claire against that container, it says it's got a version of BusyBox, 3 versions of other packages, and it will have these CVEs. So for us, did we want to do it? Probably not, but it's a customer requirement. You do what the customer wants, and their tools and processes dictate that they need it. So the image, importantly, the Docker file that describes this process looks like this. The top half is the same as before, except we add the line in the middle where we do run Dockerize. The slight change is in the bottom 4 lines here, where we have 2 layers that we essentially copy. The first is the common runtime layer, and the second is the application specific. By this being regarded, or the /image directory becoming a separate layer, this now means that all your Python-based microservices rely on the same layer within your registry, and all the C++ ones can use the same. So you end up with unique layers for application-specific logic, but only very few layers for what are common requirements for your containers. The change here is not so significant. We've taken our Python containers down another 20 megabytes to 60, and our C++ down to 95. But we've also reduced our attack surface. We've also enabled our customers to scan our containers, know the vulnerabilities, and know what it is they're receiving. So it's not as simple as just about size, but this presentation was about shrinking things, so it did at least have an impact on the size. So then I want to touch on some of the things we learned as an organization. So we wanted to, as an organization, avoid repetition within Docker files. And by this, I mean you've got 25 containers that are used by your engineers to develop and deploy software. And for this, we ended up deciding that we would use a common set of base builder images. So we defined something that would contain Python 3.4. For some of our code we haven't yet migrated. Another one that was based on Python 3.7 or latest. And the same, including the GCC runtime and otherwise. Why? Containers give teams a huge amount of flexibility. And engineers, in my experience, appreciate the flexibility, but they can also take the flexibility and abuse it somewhat and enjoy the freedom that it gives them. And as an organization, that flexibility has an inherent cost, and that cost might be in terms of how you apply a patch to a container, how you deploy something, how you deal with an incident that's been reported, and you have to work out which containers look like this, which containers look like that. So this process allowed us to give them some flexibility, but at the same time try and avoid the repetition. So what do they actually contain? Well, as you might imagine, they're based on CentOS. We're a CentOS-based organisation. Essentially, we've used it for years. So these are no different, based on CentOS 7.6 or 7.7, whatever the latest version is. In there, we ensure that we've got a standardised version of Python or the GCC runtime. And this allows us to ensure that all of our Python-based microservices are based on some version of Python that is common. We've allowed for the fact that some are based on a 3.4 and some are on 3.7, but we don't have ones in the middle. We don't let them have different minor numbers. We've just gone, there's code that was 3.4 that we haven't got round to migrating, and code that's 3.7, which is what we're sort of moving towards. And the same is true for the GCC, glibc. You know, pick all your version numbers, align, stick with them. And we ensure that some of those examples you saw earlier in all those Docker files, you could see us adding the same Nexus repository information, the same kind of certificates, the kind of stuff that every engineer will just copy and paste. You don't need to, because Docker gives you the flexibility to just choose a different base image and have this already pre-set up. So instead of doing from CentOS 7.6, we can do from Python Builder, making us focus on what we felt was the important stuff, which is our configuration and our application-specific logic. So you might ask, well, what are we going to do next? Well, we're always looking to do better, as I've described throughout this. Everything we're doing is a journey. We're nowhere near the end. I think the talk this morning, it was talking about the White Tower or the White City on the hill. It seems to be moving away, but we're trying to move towards it. But every day we're learning. We've got people attending conferences, picking up best practice, hints and tips, and then coming back and trying to apply that to what we do every day. But I want to call out a few specific things to you in the room so that you can see some things we're looking to do next and how, again, they might be helpful for yourselves. One of the things we're trying to do is, as a result of ensuring we've got common base images and a common way of building Docker files and focusing on the little bits within each of these containers that provide the application logic, it has become significantly easier for us to take a step in the sort of direction of security, which is we don't want each of our containers to be running as the root user. Numerous examples of why that's a bad thing, and some of the talks I attended in September with people like Control Plane will really scare you. But in the next release, we will have all of our containers not running as the root user. And because there's not a huge amount of repetition, a couple of changes in our base images has enabled much of this work to take place. Security management. This is a huge challenge, and there are different approaches on how you might do it, what tools you might use, etc. Again, the use of common base images ensures that you've got a subset of packages to worry about. It's bad enough dealing with security without having every container having a different minor package version of Bash, and then you having to report that you've got 20 versions of Bash in production. So by dictating and using fixed versions of BusyBox commonly across all of our containers, security management becomes a headache, but not an unmanageable headache. We're also looking at things to shrink our containers further. You sort of get a bit addicted to making things smaller. I can do better, I can do better. It becomes a bit self-fulfilling. So some of the POCs that I've done with a couple of the teams and various hackathons have been using a program or a package called PyInstaller, which I'd recommend. It's pretty easy to use. But essentially, you can compile Python code down to C code, and then it can apply many of the techniques that we talked about earlier, where it strips out unneeded symbols using standard C tools, and makes your Python code significantly smaller. It also has a couple of other sort of useful side effects. The first, your Python code is no longer plain text in a container. It depends how much clever stuff you're doing in Python code and how much clever stuff you want the customer to have access to. But if you remember back to the beginning where I said we've given BusyBox in all of our containers, it's not impossible to get into our containers, and plain text Python code might not be the best place to hide anything that's unique to what you do as a business. This at least provides some level of obfuscation. We're looking to change our container entry points. Now, this might look, well, what's this got to do with shrinkage? And it's pretty simple. At the moment, we've got BusyBox in our containers, and it provides a shell. As you might imagine, when given a shell, engineers have a habit of using it. So the entry point for many of our containers is some kind of shell script that runs this and that, and then they get into a nasty habit, oh, I can run this in the background. Really? This is meant to be one thing well. But as we move forwards, we're looking to change to using standard things like config maps, and then a single binary and a single sort of microservice entry point within our containers. What that will enable us to do is actually then potentially remove that shell from the container and remove the BusyBox. We're not there yet because we're still at the stage where having BusyBox is more valuable than not having it, and therefore why would we start to optimize already? But that's within the roadmap, and increasingly our customers, as they become more security aware and their IT organizations ask, why have you got a shell to every container? We've got a plan of how to deal with it. Another thing that's been flagged up in a couple of the other presentations, well, we've done this ourselves. We're not really in the business of repeating the work that everyone else is doing out there, and some organisations are significantly bigger than ours and have significantly cleverer people in certain areas working on this than us. So our base images that we've created look a lot like what you might see if you go to Distroless project from Google, where they've got, I think, a C one, a .NET one, a Java base image, where they've essentially said, can we have an OS-free container and a process to build it? And they've got a test framework around that. So we're having a look at that at this moment in time to say, instead of maintaining our own base builder images, can we rely on something like Distroless? And the advantage here is it takes away some of our responsibility, and it places some of the, we have to check what's coming in, but we've got Google guys looking at security for their Distroless and a wider set of customers using it, reporting vulnerabilities. So the likelihood is that user base using it on a daily basis will be inherently more secure than us trying to do it ourselves. And there was something in the news earlier in the week about Alpine and how people just rolled it themselves, and then there's some root vulnerability. These are the kind of things that will just happen, and as us as an organisation, we're not interested, if you like, in that OS level. We want to ship stuff that does video to customer and rely on other people to provide some of the other logic. So I'm going to conclude with what I say are my 3 key lessons, or the 3 most important things that we've learned on our journey. 1, it is possible to take an iterative approach to taking what you might regard as a legacy platform, a monolithic piece of code on a CentOS-based server, and look to move it to the cloud. You don't need to throw it all away. You don't need to start again. And I can get the buzzword in. You can do it in an agile fashion, iteratively delivering improvements to both your customers and, for my engineering teams, taking management with them and realizing it's not this great big, like the white city on the hill that's never going to be achieved. You can actually demonstrate value along the way. Secondly, remember what it is that you're actually delivering. I very much doubt whether you, much like we, are delivering containers to customers. Containers are just a thing. What you're actually delivering to your customer is some kind of solution to some kind of problem they have. So don't focus on optimizing your containers unless it's actually optimizing the solution you're delivering to your customer. Otherwise, it just becomes an engineering game where you're just optimizing because it's cool to do, but you're not actually adding any value to the organization. So focus on understanding what you're giving your customer and how you're going to make that better. Thirdly, I could say most importantly, keep up with the technology. When we started this, there were a number of orchestration platforms you could use. Now, there's still a few, but it seems to generally be either Kubernetes or some kind of OpenShift, and that's it. Whereas in the early days, there were a number more. How many runtimes are there? You can try. So keep up, get people to attend these conferences, take the best practice, and constantly try to at least understand where it's going. Otherwise, in 2 years, you'll have to make another big jump. And more importantly, and sort of call it out again, there are a huge number of examples on the internet about how to do things better with containers. And if you start typing it in, your Google sort of search bar will get overloaded with all the different ways you could do it. But remember, there are other people and other techniques from other industries that have done things that, if you think slightly outside of the box, might be applicable to what it is you're doing. In our case, if you're trying to make containers smaller, we recognise that we could use embedded software techniques to achieve that. And if you Google for those, you get to some hits generally quicker than all the hype, if you like. Many people have spoken about it in the conference today, that overtakes you with all container stuff, whereas you get straight to the point. So look around at what other industries are doing and how you might use what they're doing. For us, our embedded history has been invaluable in getting us to where we are today. And that, hopefully, roughly within time, is me. Thank you very much.